Thank you. Paul?
Yep. Thanks everyone for coming to the Alberta chapter of the Institute of Navigation. Today is I think the 6th presentation that we've had this year, and for those of you who come every time, we're planning to try and squeeze in another one at the end of November, and that'll probably end up being our last meeting of the year. Before we get started, I'm going to go over a few ground rules. So please keep yourself muted during the presentation. If you have any questions, feel free to use the chat, and you can either direct questions to myself or to everyone in the chat, and I will facilitate those questions to the audience. If you'd like to speak for yourself, just raise your hand or unmute yourself when we get to the question period at the end, and I'll call on you, and then you can ask your questions and have your discussions. So I'm very excited for the speaker that we have today. Dejan has a PhD from the Leibniz University in Hanover, Germany. He has over 25 years of experience in geodesy and a deep love of robotics, software engineering, and algorithms. Don't trust programmers that carry screwdrivers. He is currently a professor for measurement technology and mechatronics at the University of Applied Science in Rapperswil in Switzerland. And today his presentation is towards autonomous field systems and smart farming. So over to you, Dejan. Thank you. Thanks for coming.
Thank you, Paul. Thank you, Kai, for the invitation and for the introduction. Yeah, don't trust the programs who carry screwdrivers. I'm sometimes carrying also a wrench. Just for the wording, we on the 1st of September we had a joint venture with other 2 universities in Switzerland. So we are now University of Applied Sciences of Eastern Switzerland, which is much longer than the HSR, and we called Austin in Swiss, or in German it's like East. Well, we don't sing go west, we sing go east. So now, I would like to greet you from the most beautiful campus in Switzerland. I can say that it is really great here. We have lakes, we have mountains, and we have approximately 1,600 students, which most universities maybe laugh about it. But for Applied Science University, we are quite well suited. So we have several engineering courses, and I'm a part of the mechanical engineering. So it's kind of weird that the geodesy is in mechanical engineering, but you guys, if you know how to program and basic algebra and everything else is just kind of investment time. And I'm really interested in robots. So you will see that why, because sometimes I say I have the most beautiful, most interesting job in the world, but each professor will say that. And second thing, my English is bit rusty, so if I sometimes use not very common words for certain things, well, just forgive me. So let's get started. What we're doing today is I'm going to try to give you kind of an introduction into farming. Not that we were going to do any kind of herbology or anything, but nowadays, we know that the production of the food and everything takes really a lot of resources of our nature. And what we want to do is to show a use case, a quite complicated use case, which can be then scaled to the bigger machines and help us to get to that we get autonomous systems working on the fields. So the conventional farming is on the edge of the change. The paradigm changes. The paradigms changes in the food production and also environment protection, especially in Europe. Each farmer has to do some kind of a weed control, and they do it nowadays with biocides or herbicides in this case. And they are searching desperately for new tools where they don't have to put the poison in the field. Then automatic weed detection, that's a topic which is more or less old as a computer vision. And we know in 50s, people thought that in 10 years, we are that far that the computers will think as humans, which we still don't have this kind of a case. But what we do now is that we have now technology and a computing power to put new generations machines on the field so that we can achieve a similar productivity level as the conventional farmers do, but not on a very, very large fields. This is still a domain of the conventional farming. And I will show you some building blocks of our autonomous weeding system and the challenges which are there. And there are not few, there are many. And then I'll give you a little glimpse in our new project, which started this autumn, how to make money with weeding system. So yeah, let's see first, what is the conventional agriculture? So I've chosen these images randomly from companies Claas and John Deere because they have really beautiful images. But especially in a North American continent, the conventional farming is big, just big. There are wide areas. This is like a seas of the wheat or corn or anything. And you need huge machines to really do the processing in the field. Those machines, they're big. And if the farmers must sit for such a long time on such machines without any assistance, that will be also very tiring work. So when GNSS helps those people to fulfill their task almost autonomously, but still the conventional farming is, let's say, #1 poison in the environment. And in Germany, the farming is second worst carbon dioxide producer in the whole country. They produce approximately 8% of the carbon dioxide footprint, and only the energy sector industry is producing about 70%. So the next step is farming. And then what I said, we have a weed treatment, which is actually spreading the herbicide in the field. So what you see here is a new machine from the company AgriFac, which has smart nozzles. And those smart nozzles just apply herbicide on exact spot where do the recognition of farmer. When the farmer says, now do this on that spot, this is where you're going to apply the herbicide, then they do the application. So they use GNSS antennas to precisely or accurately determine where is the weed located, and they spray. And then those spray very, they are not, let's say, saving the poison, the saving herbicide, they're spraying quite a lot. You can see that almost the whole field is wet from the application. So this is called precision farming. Well, precision is if you can see a ½ meter wide, so that you still get the plant or the leaves going to be processed. And on the end of the day, it saves maybe like 30% of the herbicides during that procedure. However, it's an improvement. Now, each farmer have to make a decision. Am I going to do the conventional farming, or I'm going to do organic farming? Conventional farming allows big scales, a lot of production, a massive food production, or whatever kind of production is needed. And with the mechanization or automation, which I just showed before, those farmers can really get produce for very low money amount. We'll see why. The field machines are all steered by GNSS, and companies like Claas and John Deere, they cover the whole chains from the planning, seeding, plowing, weeding, and then harvesting. Everything there is made just to be as effective as possible with as less human interaction as possible. So they are assisting systems. They are big. They compact quite strongly the soil. And the farmer must produce more and more food or more and more of his products to keep his enterprise alive, since the food prices are very low. And there is no trend showing that the conventional food production will in anyhow that the prices are going to increase. Just a simple comparison. We have on the left-hand side wheat prices. And then on the right-hand side, copper prices. And nice would be like a demand, how much of that, how much production or how much wheat will be consumed in the world. But we have here 1970, and the price was like, let's say $6.50 US. And we have year 2020, which is today, and we have still the same price for the wheat. So if we compare that to the copper, we see that the demand with especially with the computer devices and the small mobile phones really just jumped on doubled, and then stays more or less for the last 15 years at the same level in average. So it means it's better to actually get the copper out of the ground than grow food, which is quite, let's say, sad. Even more astonishing is that if you see where the wheat production actually happens, especially in North America, where the labor prices are not that low, like in Southern America or Africa or China. Still, Russia produces also a lot of wheat, and the labor there is much cheaper. But I mean, $6.50. This is, and for what is that? 50 years. This is kind of weird. Everything gets expensive. So the farmer still must make this decision: conventional, so go big; organic, you can do smaller, and you can get better margin for your product. So the profit margin is higher because the people, and it's considered like a luxury, want to eat healthy. So there is a large need by the farmers to create to have a same mechanization as the farmers in a conventional agriculture have, but to be as productive as them, but still use no herbicides or biocides in their production. The other thing is that also the conscience of those people gets better, because they can actually say, look, I'm not polluting the environment. My carbon dioxide footprint is low. We have animals welfare. We have happy cows. We have happy goats, and so on and so on. Then the risk of getting very sick because using of the chemicals and everything can be avoided if you don't use them. And the work-life balance should be also a little bit better, because you don't have such a big fields to do. And then the people from rural environments, they want to buy from someone who is near. So they say, okay, I want to talk to Urs or John, who is producing such a good tomatoes. I want to buy them from them. So, but if they want really to be competitive, they need completely an additional level of automation in the field. Now, what can farmer do? He can do like arable crops, which are really these large fields like sunflowers or wheat. He can do vegetables or olericulture. So this is a kind of a little bit more trouble, a little bit let's say not so easy to harvest. So you have a lot of manual labor inside. Or you can produce meat, which is nowadays also a little bit bad, but still you can just put the cattle on the meadow, and then they can you can sell the meat there. So it's a quite good income for doing this. So, but if it comes to wheat, and the farmer has to assure that the wheat is not competing with his product, then he cannot compete with a conventional farmer. A conventional farmer can do a 5 hectares within the hour, and an organic farmer, he needs like a week for that. So how can we enable that? So let's do it a little bit animated. So whenever we get on each of the sites, we get weed. And weed control is crucial for any cultivation art. It's almost as important as fertilization. And if they fertilize and have a competitive weed, then the weed will also grow faster. So we need to keep the weed as low as possible for as long time as possible. And while the weeding in the cultivated area in the field where you have rows and everything is a bit more easier than in the grasslands, since in the grasslands you don't have any grids there, or you don't have any kind of the order, then we have to see that if we solve this problem on the grasslands, then we can scale that on the field too. So we started that in 2006, and we thought that in that time that active sensors, so a vision camera is no go, they give us more reliable data, more accurate data. With passive sensors, we shouldn't go there. Then we had a good effect if we have a third dimension, that we can actually better segment objects from the image. We can estimate the surface of the objects or leaves in the area, because then we can distinguish which plant is what, based on the shape of the leaf or of the patch what we're seeing. And then with that, we can also see the certain features on the field which are not actually seeable on a simple vision camera. And we use a lot of hard-coded algorithms and manual feature engineering, which I'm just talking a second. And we saw no GNSS necessity, so it should be kind of a real-time system. Now, how was that? So we use a flatbed scanner to get our samples. So we used the flatbed scanner, then we created a blob. Then from that blob, we extracted the border. And the border we analyzed with the elliptic Fourier descriptors to retrieve the feature vector. So for each kind of the weed leaf, we got that kind of a vector, which was varying depending on the shape and the health of that object. And then we could actually compare those different shapes just using the border. And the border or of the wheel, of the leaf, the blade, that must be as flat as possible. So that's why we use the 3D to flatten those. So you'll see how it works. So we had the different leaf shapes categorized in 40 classes. And then we did the analysis, how much and how good those shapes can be distinguished between each other. So simple analysis, Hanobi's distance between the leaf shapes from those feature vectors gave us a quite astonishing results, that if we compare those 3 leaf shapes like seeing here, then each leaf shape with itself has the shortest distance. So we have the dark red. And then we see that those which are similar, they're really kind of near to each other. So there is no big difference between them. So that was a kind of a good sign. All right. So this distinction between the leaf shapes is a kind of a bad. It's promising. All right. Then we saw the features. So these elliptic Fourier descriptors, they give us just like a power spectra of the curve. And then we saw, well, the correlation between those features is not big. So the first 10 are really good to do the discrimination. And the rest of them, they have such a high correlation that we might want to neglect them for our machine learning. Those days we use the support vector machine, that it might actually make us more noise or more trouble than actually use. On the end, we used 35, and that was kind of a middle decision, just let me see. So that we stopped actually at that spot here. Now, what was the biggest advantage of the 3D system is that we were able to extract leaves from the 3D data as they are in the space. And we could, using the differential geometry, we could flatten them as good as possible to become a flattened scanner-based leaf. And then we were extracting the boundary of such leaf and then compare them to the scanned images in the from what we had from our scanner. Now, this was looking like that. What you see now, it's experiment, I think 2008 at Agroscope in Tennicon, where we had a machine. My screen is okay. So these are our weed leaves here, and you please watch the nozzles if you can see them. You will see that it just switches on and sprays on a certain spots. So this means that this vehicle which you see now, this was our Borg vehicle. I told them because it's a kind of a cube, and it was like 300 kilos heavy, and we had a really strong laser inside, so that everybody had to walk with our glasses just to do the measurements. And we had to also cover everything from the sunlight, because sunlight was interfering with our laser, and we got really weird results. So when it worked was perfect, since this is exactly the data from the experiment what you see before. You can see that the surface patches are quite good, quite homogeneous. We could extract the leaves really very well. We had really strong response as soon the sunlight was not in a game. And when we analyzed that, the algorithm was able to extract the certain patches depending on their size and orientation. And then we extracted the boundaries, and then we got the matching, and some things where they really very near to each other, they didn't fulfill all the conditions to say, okay, this is a kind of weed leaf. But when we discovered at least one of the weed leaf, so we could say, okay, in this area, the other candidates that might be also there. So we were really detecting more than 85% of the plants by detecting more than 65% of the leaves. So it was kind of, let's say, disappointing. Disappointing was also that we didn't meet the speed which was necessary. It was 1 meter per second, so we were like 0.7 meters per second. And what we had trouble with was the computation power in the field. Yes, that was really a showstopper because our computer wasn't able just to process the 4 GB of data per second doing all these computations. And yes, the sensor lacked of the reliability. So that's why we actually thought, well, that's a nice idea, but we have to wait for better sensors. And the commercialization of such system was, let's say, impossible. But then there was a renaissance in the deep learning in 2013. The general purpose GPUs arised. So, and 2018, we kind of have a bird of the weed eraser. So it's a kind of a smart reader to weed eraser. Well, maybe once in a while, all the names are going to be used somewhere else. So when I started at HSR in Rapperswil, we actually said, okay, now we have to start doing this properly. So we designed, okay, what an autonomous system in the field needs. If we go from the mechanical engineering point of view, so we build a completely new machine. So if we have adaptive intelligent machine, then we need approximate weed coordinates, approximate weed area, depending for the treatment. Then we need a situation awareness to see what's around us, maybe a cattle or a farmer. So that's therefore we need this kind of a system intelligence. And all that stuff is kind of approximate. So if we want to build this, we shouldn't go for a really some kind of a millimeter chase. We want to go for approximate system so that we can build it cheap. Now, the idea was born. So the carrier vehicle, this was stolen from the Carnegie Mellon University, is our UGV, unmanned ground vehicle. It's a carrier platform which carries the manipulator, robotic arm. Then we have a field sensor, the ground sensor, which is in this case just a mock-up of the camera, but also we have also other sensors there. Then we have a air segment, which is our UAV landing platform with the GNSS receivers and where the UAV can land and start if the system tells them. And then what we use the UAV for is to increase the efficiency of searching a weed on the grassland. And we are certainly not the first guys who have this idea, but we are probably the first group who want to build such system for $5,000 US. Okay, I'll give it for $4,999 because this kind of sells better. I've heard that. So we want also to build affordable, versatile, autonomous weed system, detection and treatment system, which can be also provided as service. So maybe a company provides a service for farmers, and we also want to use the newest technology, the 5G mobile networks and cloud computing, so that we don't have to put as much computing power on the field, since this requires also a lot of energy. So this is a vision. What we had. We had a workshop in Ireland of ICT Agri, and then collecting all those requirements, then this idea set up. So let's say following. So we need an infrastructure. It's a kind of good mobile network coverage. We need a cloud computing for that. And then we need our system consisting of the ground vehicle and UAV. So please imagine this UAV just started here and is in the air, and then it will fly over the meadow and acquire data, image data, multispectral data, whatever. This data will be then transferred via 5G networks directly to the cloud, where we have our inference system and a computing power. So then we run our neural network system, and this neural network system sends us over the 5G to our robot there the coordinates or approximate positions of the weed. So all the time the cows and the farmer are in the field, so they are not disturbed. However, the system tells also the robot, look, on these spots you have a livestock or you have a human, so if you travel you should immediately do your path planning so that you don't endanger these species on the ground. So you are kind of a guy who shouldn't hurt anyone. So then the robot starts, goes through the area, treats every single weed for whatever part that, and when it's finished, sends the data to the cloud that where the weed was treated and where not. So if we did that well, which we do, then the weed will disappear, but some of them will come back again. But since we have the coordinates of that weed, then we can come back and do it again, or wait until the animals are away so that we can continue this thing. So, but this is what we can do repeatedly if the system is autonomous. Now, since 2018, we are continuously realizing our vision. So we did a lot of work, and we built certain blocks which we can go for our aim to have a $5,000 system. We use a low-cost GNSS navigation based on U-blocks. Sorry, Paul. And this gives us good RTK performance up to, let's say, 2 kilometers. And we can say we are navigating 20 centimeters accurately. Then we use a ROS, open source robotic system, operating system, for integration of our components. This gives us quite a push when we develop the components. So because it's completely independent, it's a sandbox architecture. And then we also integrate a low-cost inference system for an NVIDIA. It's approximately $700 system, but it can process 280 frames per second using the deep stream and deep learning algorithms. Now, our carrier vehicle is everything but not low cost, and robotic manipulator is not low cost, but it's actually a research unit. And hot water treatment is experimental, but we have really promising results. With all these things, we will have a really good system. So let me give you now my highlights. With two students, Matthias König and Damian Schori, they did a deep learning phenotyping process. So the redetection was the greatest problem what we had. And between 2000 and 2010, we were struggling with the detection rates about 60 to 70%. Then we got the 3D data, so we increased that to 80%. But still, it was not satisfying since we didn't have correct sensors, and all the sensors were very expensive. And then we had a deep learning revolution in 2013 with TensorFlow, PyTorch, and all those guys. And then suddenly the detection rate rise to 95% plus. And this is when you can start the commercialization. So the student, Damian Schori, did in his thesis in 8 weeks, he used the UNet-based segmentation algorithm, so semantic segmentation algorithm. He adapted it for the Rumex and achieved that he can detect 95% of the leaves correctly in the meadow by the resolution of 500 times 500 points image, which was until that not possible. What you see in this image now on the right-hand side is that the ground truth is kind of pinky, and the border, the cyan border, what you see here, it's the border which the detection algorithm says, okay, those pixels belong to Rumex. So in non-optimized state, we can process approximately 4 to 5 frames per second, depending on a pipeline or a computer. But with deep stream tools from NVIDIA, we can approximately process 20 frames in a 48 pixels image resolution. Since the 250 frames per second can be processed, so we split the image in several times and then do a massive inference on that. The plant roots, which we need for a hot water treatment, you don't see in any of the images, but we can locate that approximately at 3 centimeters accuracy. You will see why is that so necessary. These are some results of our detection algorithm. As you can see here, as a yellow spot, this is the ground truth. This is where the human said, okay, there on that spot is a root. The black spot here is the one which our system found as a root here. So we have ground truth, and this is where the algorithm said, okay, here it is. And here we have a double recognition. So the black spot is now hidden behind the yellow one, but somehow it found that there is also a Rumex here. So it's not a perfect, but for 8 weeks of thesis work, it's quite astonishing. So why do we need this few centimeters accuracy of the root? If you want to treat weed effectively, we have to actually kill the plant by doing the hot water treatment. So we have to boil it, more or less. And this hot water treatment was developed by Roy Larch and Joachim Sauter from the Agroscope. And they used the high pressure cleaner system to experiment to how to treat the weeds. Now, they achieved mortality rate of about 80%, which is okay, with water temperature a little bit higher than 80 degrees. And they needed 1.6 liters of water per plant. And 1 liter of oil of the fuel needed we were needing for 50 plants, and this is because of the heating unit. But they needed 10 to 15 seconds. And this spot stream rotary nozzle is the one which is really necessary because it breaks the ground and propagates the hot water into a root. And we have to dive as 15 centimeters deep and then actually boil the plant of that. If you get the temperature above the 60 degrees, the plant dies. Then they optimize that unit with the 2 nozzles and rotating system, so that we actually can kind of drill the hole with a hot water seam, and we have like 130 bars or 13 megapascals at 90 degrees Celsius are coming from those nozzles simultaneously. Now, we are developing new, more convenient treatment unit, which will be much faster, and we assume that we will get 5 to 6 seconds time. We will be able to kill each of those weeds, and we can scale it in a size. So, and now what we also developed as a student work, we developed a new SCARA robotic system, also ROS-based, where we can use this arm to position that over the plant. Why we did this is the navigating 900 kilos vehicle 3 centimeters accurately over the plant is kind of tricky, especially if you have Akamar steering and so on. So it's not very convenient to do this. But what we can do, and they couldn't go into field, so this was kind of proof of concept if the arm is really positioning very well. So also what we have a COVID-19 concept of route tracking developed by the Damian Shori and the same student which you've seen before, is that we are able to track the routes from the video. So that means that we can use the very cheap system like NVIDIA Jetson Nano or any other inference system to track the position of the route in the image, and with a certain information, maybe a 3D time of flight sensor there, we can actually project that in the robotic arm space. And having that projected, so we can do these detection also online, so without the UAVs, but also what we can do is to accelerate the processing time, since we position the car, our vehicle, near the plants, and then we can do processing on each plant with robotic arm. This makes the whole story much easier, since we have a reach of the arm approximately 1.2 meters. This robotic arm can stand 800 newtons of force, so it's a kind of a robust technology which we need in the field. And we can put 40 kilograms on the tip, or on the tool tip. So we have also sufficiently fast robotic arm. It can move not very precisely, but fast enough that we can actually say, all right, we have a proof of concept. If you want to do this on speed and weight optimize, then we have to start another project. But still, we are able to position the TCP, a tool center point, using this static camera visual servoing system that we are really above 3 centimeters above the root of the plant. So the main gain of this is that the vehicle doesn't have to navigate 3 centimeters accurately. So, and yes, our vehicle, it's actually, how we call this, pimped up golf cart. It's not pimped up. We actually moved everything away and put our steering units on it, GNSS camera, the linear axis, brake and steering control on it. with all these controls and everything, we invested 1,600 and 585 Canadian dollars in this machine, and we paid for the machine, or Agroscope paid for the machine. It's approximately 1,200 Canadian dollars. And if we would buy those elements for a price of as industrial partners, it would be kind of double price. But 1,500 hours students work, and we have a position accuracy of 3 centimeters, so we know our position and orientation of 3 centimeters accurately. But we don't need, you don't need that, because we need just 30 to 50 centimeters, depending just when the occlusions come and so on. So it's not a big trouble, because our Sky robotic arm can do this. Also, our biggest trouble is strong EM interferences, because we have 400 volts here, and the controls and everything here, they interfere with the GPS signal. And really controlling this vehicle autonomously when it drives over the meadow, it's really challenging, because the speed is really challenging, because it works mechanically, but we are mechanical engineers. And then we have another weak spot if we want to make this stuff, let's say, more convenient, more faster. If you want to do that with the UAV, the detection of the video camera of the weed, then we have to do this really on the height approximately 30 meters. And if you see those videos here, I'm sorry, but my computer is now boiling, that if we rise a height, that we lose a lot of information, since the resolution is not sufficient. So this is what we want to see from the height of the 30 meters, but what we get is actually that. So our algorithms works perfectly on such images, but on such images, it fails. And this is where we are going now. We are working exactly on, at the moment, I think Benjamin is in the audience now. He's working intensely on that to see what can we do. Because we want to use commercially available systems. We want to use off-the-shelf components, because this makes the stuff, our system cheaper and more convenient, so that we can spread it around. But we have a lot of open issues, considering the motion blur and image resolution, autonomous UAV, so that it can fly away autonomously and come back, UAV-UGV interaction. And also what we need is a end-user friendly interaction interface and interaction procedures. These are, it's kind of an engineering interface. And in the end, we want to retrieve a cobotics, a system that actually can work with humans together without any trouble. And we want that our industrial partners make money with this. So how are we going to make a weed treatment, autonomous weed treatment, as a money maker? We started this project this autumn, and we are in the first step of realizing our vision of that. So we are focusing in this space not just on the technological aspects of the project. We also go for the economical aspects, and we got money from the Swiss government for that. And we have a really important partners as FENACO and Sunrise Communications that we can realize that system. So the first idea of bringing cloud to the field is that we will acquire the data with UAVs. We will transfer that data over the 5G, do the processing and localization, auto creation in the cloud. And then we will transfer the mission file to the conventional machine, which will do then spraying in a millimeter accuracy. We are just, at the moment, we are developing the special nozzle. What we will do also, we will have a map of detected weeds, so that in the next period of time, we can search on those spots where we already detected those weeds, and then see if our treatment was well, so we can self-evaluate ourselves. And we hope on the end of that project that we will be able to have a kind of autonomy there, so that we can switch from the manual, organic or semi-organic weed treatment to automatic weed control, or let's say at least humanly assisted weed control, where the farmer just sitting in a sun chair, drinking his beer, margarita, or water. And if the system needs something, just tells him, sends him a message, look, I don't know if this is a weed, can you tell me if it is, so I can treat it? Otherwise, I go to the next weed, which we can do with this technology nowadays. And then from the farmer, which is kind of married with his field, we can make it some kind of a Roman emperor. We can say, so, okay, this plant lives or this plant doesn't live for the next few weeks. So with that, I'm on the end of my presentation, and thank you very much. And I'm ready for the questions. Paul?
Great, thank you very much, Dan. That's very interesting. So for anyone who's got questions or wants to answer questions, if you unmute yourself or raise your hand, then I'll call on you so that you can answer your questions. Otherwise, if you're feeling a bit shy, you can write your questions in the chat. And while you guys are preparing your questions, I'm going to kick off with one of my own. So so when you switch, you said you needed like 30 to 50 centimeters of positional accuracy in the vehicle on the ground.
Yeah.
What are your position accuracy requirements once you move to a UAV, and what do you think is the best way to achieve that?
Well, the point is that the UAV is a kind of a trouble because usually you don't have fiducial points or any kind of orientation points on the field. We don't put landmarks on that. So the photogrammetric part is really challenging. Now, when we do this, we are at the moment we are pursuing two ideas. We just say, okay, the weed is within half of the meter, and then the robot goes there and treats the weed, because in the moment when we are there, it's going to work. But for the conventional kind of farming, we need that high precision. Then we will need a drone with a really high level RTK GPS. And we will also have to do certain things on the field that we at least can orient our orthophotos in the system, that we can achieve that 3 centimeters accuracy. So for the experimental area, we will use probably moving landmarks, so which we will do more or less with a RTK GPS receiver. We just put them on the field, we mark them, and then we fly the session with the UAVs. And then when we finish that, then we will process and find the best solution. But at the moment, beside the resolution, this is also the big challenge.
Okay, thanks. Yeah, there's a few questions here. You mentioned at the beginning that you were relying on LiDAR imaging and the RGB was a no-go.
Yeah.
Yet at the end, it seemed you were using HD images from drones. Are you relying on both now?
No, we neglected the LiDAR completely. For several reasons. LiDAR doesn't give us a structure of the leaves. And now we are completely switched to the classical vision deep learning system because it gives us much more reliable results. And with LiDAR, we had also a problem, like whenever you have panoramic distortion there, when the vehicle moves, you have shifts in that. So we had the resolution problems also in the peripheral area. And then combining all these images, we had a lot of noise in the cloud. So we had to smooth it and so on and so on. With a camera now, I mean, a good camera for this, it doesn't cost nothing. I mean, you can use your mobile phone, go there and take a video with that and run it through our system, and you will get 80, 90% without any pre-processing. So we switch completely to the vision. And this is why, with the advance of the deep learning, we are hoping now to really to make a product. So we are not at the basic research. We usually make our projects are all with industry, and we have to pursue that they need, in the production, you need less costs, and then you can sell your service or your system for more money.
So it sounds like the advancements in deep learning and artificial intelligence has really allowed you to switch to a camera away from LiDAR.
Yeah, we can now experiment, with our systems. We can, in the night, we can run all this inference through that and see how our training perform well. So we have a really strong group with machine learning here in Rapperswil, and those guys, they have DGX2 NVIDIA machines. So the training of our networks takes now not weeks or days. It is a matter of hours, because we don't have such really very deep networks. We use always transfer learning. So we just train our soft layer and maybe the top one layers to really get those features which we need for our weed.
Mm-hmm.
And we
and
can
maybe just for the people that aren't aware, so that the training operation, which takes a long time, is different than the operation that would do detection live on the field, right?
Yeah.
So do you have any speed issues with immediate detection on the field, or is it just the training that takes a long time?
Oh, the training takes a long time. I mean, we can process really when we use this NVIDIA deep stream. This is kind of a software stuff. When you attach the camera, you stream the video through the software, and it can even the smallest one system can actually process 16 images per second in a resolution of 300 times 300 pixels. And what we have high resolution images, which are 48 megapixels. So we will have to split them in several frames and then run it through a bit more stronger. So it's $600 expensive Xavier AGX. And then we can process 250, 260 frames per second. So we have a real-time performance. Mm-hmm. And also we verify that. So you can use, for example, this Intel RGB stereo camera, which gives you also 3D point cloud there, so you can actually do that. I mean, it's 10 years now, and it's just amazing.
Cool. Yeah, there's a bunch of other questions. What sort of duration is the system expected to have, and how do you intend to manage refueling, recharging, and also reloading consumables?
Okay. Now, our goal, or what are we aiming for, is to make a system that actually can work for 1 or 2 hours on the field. So we expect with a robotic arm and everything, that we can process 2 to 3 hectares in 1 hour. So all the refueling and consumables like hot water, fuel, whatever it is, this has to be dimensioned in the next step. First, we aim for this very fixed part, and then we are going for scaling. The biggest energy consumer is the hot water. This is what takes the most of the energy in our system. And also water is very heavy. So if we want to transfer a lot of water, then we have a bigger machines. So this is a really challenging part. What we don't have, we have to do like one step after another. First, do the treatment, have it for an hour or 2, and then we'll see how we have to scale this. So no, we don't have a plan now for the complete chain.
Okay. Someone asked, used to take, I think you had mentioned, a week to control the weeds for organic farms. Has this time been greatly reduced, and by how much with the latest smart robot? I think one of the main benefits here is that it doesn't take any manpower, right? It's all automated.
Yeah, it is. That's the point. And the robots can work 24 hours, 7 days a week. What we are, doing now, we are trying to purchase a Boston Dynamics Spot, which is a kind of small robot. But this one has a kind of solved a lot of problems. So it can walk on the areas where the humans can walk too. And we will go for that and see how can we actually use that robot which can go and recharge himself by itself. So to see that we use this technology then for our weed treatment. However, it can just carry 14 kilograms, so which will be challenging for the hot water reservoir and something and all other things. But we are just going in several directions now to see, okay, what exactly is necessary, and then do one step after another. I know that it sounds now repeating myself, but it will save the farmer a lot of time, because 40% of his time he has to take care of the weeds. He needs a human power, especially the organic farmer, to do all that all the time. So this is kind of a continuous part. Now, it's going to save it, yes. If he have to do this, he will be able to do other things. We also didn't talk about insects and all and everything else. So this is also the story. I mean, the biggest advantage of the plant is they don't move. So it's easier to find them there. So the insects like snails and all the other cockroaches, what is it, those jumpers?
Grasshoppers?
Grasshoppers and so on. So, you know, that's much more challenging. So we still now, weed is the first step.
Mm-hmm. You mentioned that the resolution of the photos from the drone is not sufficient for the weed detection. What avenues are you exploring to overcome that problem?
So not the biggest problem is the resolution. Now you can buy a DJI drone with 48 megapixels. So the Mavic Air 2, it has 48 megapixels resolution. Our biggest problem is the high frequency motion blur. Through the rotors, you achieve such a high frequency rotation so that there is after a certain height, the lot of those features, they just disappear because of the motion blur. And it's also rolling shutter sensor. So there are certain things there which are not so optimal for our process. So we are now, first of all, we are looking for the camera with a global shutter, the optics, and the weight reduction, so that we can overcome this problem with the rolling shutter. Then we need to decouple the camera from the body of the drone, so that we don't get this high frequency motion blur inside. Then we're going to get sharp images, because still images from the camera, from the human, on the same height, deliver 10 times better images than the drone, because just of the vibrations of the vehicle.
Mm-hmm. We have someone that'd like to ask a question. Munir, do you want to unmute and ask your question? You're showing it's unmuted, but I can't hear anything. No, unfortunately, there's no sound coming in. Would you like to write your question in the chat, and we'll try and get to it, or figure out what's going on with your microphone? In the meantime, someone put in here, I can't speak for all farmers, but for us, so I assume that Aaron Jackson is a farmer. One important thing is independence. What does this entail for farmers in terms of learning new skills, or would it end up being a situation where they would rely more on third parties to complete their own work? And what about repair abilities, for example, ties to John Deere right now to repair in the United States?
Yeah, I feel with him. This is why we're aiming for $5,000 machine. It's not just the Western countries where you have very high standards. We also want to give the chance to the people in Africa also to do organic farming. So that's $5,000 system should be available for that. So this is why we are going for all these cheap elements. So, and we also go for a modular system. So you just plug out and plug in. Our treatment arm, you can actually put on any tractor. It doesn't care who is behind that. So you just put the camera, the rod with the camera, and the robotic arm down there, switch it on, and it works. So this is kind of a situation where we are now going to, okay, which add-ons we can take for conventional machines where you don't have to throw them away. So I mean, the robot like Spot is $75,000, which is far above $5,000.
Yeah. I mean,
so this is why we're trying to get that that kind of system. Sorry, someone is talking to my ear. And yes, we are working with companies on that. So once we get into productization, then you have all the life cycle, you need the service and so on and so on. So this is let's say a long way. I assume between 5 to 7 years that we will start to have first add-ons. And then we will see how big the life cycle is and how long it takes that meantime between the failures. Yeah, this is kind of really very important.
Manir put his question in the chat now. I think this is probably be the last question we're going to take, unless you're willing to stay a few minutes after. On the 5G connectivity, what is your vision in terms of the type of network planned? Would that be a private 5G network or a network extending from the public one available in urban areas? Also, the $5,000 US dollar cost. Does this account for the recurrent cost of 5G connectivity and cloud? Oh, sorry, jumped on me. And cloud platform rental.
All right. So, well, I'm going from the Switzerland situation here. We don't have a 5G networks which are private here. They are not. They don't exist here. In Germany or maybe other countries, you have that. But what we are going to, we have a encrypted communication with the cloud. So you can rent a cloud like you service provider like Fenaco, and then you can send your images and you get your stuff done. Maybe you don't want even to have that kind of a machine at yourself, so you have a cooperation. So the multiple farmers buy more of those machines, buy a service, or buy a let's say Azure cloud service, and then install that and use it. We want to make as much as from our stuff available, like open source and everything. But when we start to do the commercialization and when we have industrial partners, they usually don't do this. They put a closed source and they want to make money with that. But I'm sure that once we have such system that there is going to be very much competition, and the people that this will develop to such ecosystem. So yes, we thought that $5,000 is just our vehicle with the software for the redetection and treatment. No cloud, no 5G. 5G came just 2 years ago and it became popular. So this is when we said, okay, well, we have to use this just to bring out the computing power from the field. For inference, there is no big deal, but for if you need geodetic coordinates of your plants there, if you need kind of a map, or you have to transfer the data to the farm association or whatever office you have to do that, then it's gonna be. But a flat rate 5G network is 50 Swiss francs a month, which is approximately $40 for $35. And you have a complete flat rate with the data, with the full bandwidth. So I don't think that this is going to be an issue. At the moment, robotic parts are very costly, and that's why I think it's more, at the moment, is that bigger issue than cloud service and 5G.
Okay, thanks very much. So we're past 1 o'clock, so I think we'll close the official questions. Thank you again, Dejan. I'm very glad that we could work you in